So our next speaker is Aaron Stover, who's a vice president and bridge practice lead for the Great Lakes region for Michael Baker International. And he's going to talk to us about I-40 Hernando de Soto bridge repairs.
Well, good afternoon, everybody. Thanks for having me here. Really appreciate the opportunity to get in front of you and talk to you about this very exciting project. So, picture yourself for a minute here. It's May 11th, 2021. It's a beautiful Tuesday afternoon. You're in Memphis, Tennessee. You're standing on the I-40 Hernando de Soto bridge. Imagine, if you will, peeking over the side and seeing this. You know, what are your thoughts? What thoughts go through your head? What's your reaction? If you're Fred Harper, an NBIS inspector with Michael Baker, you quickly notify your team, notify your clients, and close the bridge. Obviously, we can all agree that this is a very critical find and something that has to be dealt with swiftly and urgently. So with that in mind, we're going to talk a little bit about how the project team responded to this critical find. We'll talk about some of the challenges the team faced and really focus in on the three-phased approach that was used to get this bridge reopened to traffic within 83 days. For those of you that may not be familiar with the structure, the Hernando de Soto Bridge is located between Memphis, Tennessee and West Memphis, Arkansas. It's named for a 16th century explorer, Hernando de Soto, who had explored the region around the Mississippi River and was reported to have died south of Memphis. So that's where it gets its name from. The bridge opened back in August of 1973 and was initially expected to cost only about $12 million for the construction. Its final cost came in at around $57 million. It's jointly maintained by the Arkansas and Tennessee Departments of Transportation, with RDOT being the lead agency for the inspection and TDOT being the lead agency for maintenance and construction. Now, the bridge, as you can probably tell from the photograph, is a two-span continuous tight arch. It has 900-foot main spans and was designed by Hazlett and Erdahl. Now, the bridge is very significant both to regional and national commerce. It's one of only 4 interstates that cross the lower Mississippi River. More locally, though, in Memphis, 6 of the 10 lanes across the river are carried by the Hernando de Soto Bridge, and it has an ADT of approximately 60,000 vehicles per day. To further underscore the importance of this bridge and the importance of the crossing, it's located in the New Madrid seismic zone. And to that effect, you know, to make sure that this was a resilient crossing for the lifetime of the bridge, since 2000, over $200 million has been invested in this crossing to preserve it in the case of a seismic event. So you can tell the overall importance and magnitude of a crossing like this for these 2 communities and 2 states. So let's talk about some of the critical things that were established in the first 24 hours in order to make this project a success. You know, first and foremost, we brought in a very core leadership team on this project. A number of us had been faced with similar emergency situations in the past and fully understood some of the obstacles that we were going to face moving forward through this project. So in addition to that, we'd recently worked on the Brent Spence bridge fire, which Josh Rogers spoke about earlier this morning. That actually occurred 6 months to the day prior to this incident that we're talking about here today. So we brought a lot of those lessons learned from that project, from the Sherman-Minton Bridge repair project, the latter of which is really a very similar structure in terms of its behavior, and actually the same designers did that. So bringing those lessons learned really helped to move the project forward. While at the same time, it was really a few key things that we put into place. We had to get our hands on as much information as possible early on in the project. So we were busy gathering inspection reports, any plans, any information that we could get our hands on to really get a good understanding of the structure and its condition. And we simultaneously organized multiple teams of engineers to start analyzing the bridge and brainstorming solutions to the problem. So all of these critical startup activities are tremendously important, but one of the things that's often forgotten in something like this is really establishing lines of communication, not only with your internal team, but also with your external team, your state DOT partners. There's a lot of information that's flowing back and forth. There's a lot of parties involved that really need information quickly and timely, and having those communication channels set up is really paramount to make sure that the projects like this are moving quickly. As Josh will attest to, things are changing on an hourly basis out there, if not minute by minute. So really important to get those kind of communication chains established. So what you see on the screen now is the simplified project timeline for the full 83-day project. As you can see, we began work to stabilize the fracture, almost immediately. We got that phone call that afternoon and we're working on it pretty much right then and there. We also devised a strategy to start working on the longer-term repairs. We knew that this project wasn't going to be something that was going to be done in a week, but it was going to be a long-haul challenge. So you can see from the timeline up there, we started the Phase 1 stabilization repairs and the Phase 2 long-term repairs, both on day one. All in all, we engaged over 60 people from our firm from 20 different offices, almost immediately, really, to get them pulled into this project and make sure that we were not leaving any stones unturned there. So let's get back to the fracture itself. One of the important things that needed to be done was taking a closer look at the fracture. Obviously, once it occurred, the bridge was closed to traffic. It was being monitored by RDOT through both hands-on inspection and photography. Both RDOT and Michael Baker used drones to monitor and scan the rest of the bridge to see if there were any other defects that would be of a concern that we needed to be taking into consideration before launching into the repairs. But we also needed some additional measurements and a really better understanding of the fracture before we could really proceed with the repairs. We had to understand that condition that was out there. And that's where Jeff comes in. Jeff is one of the leaders of our rope access team, and he volunteered for this mission to go out there. And, to really take advantage of Jeff's inspection out there, what we did was, it was kind of an innovative approach to this. We used the drone and Jeff we set up a meeting, essentially a WebEx meeting, if you will, or a Teams meeting, whereby we took the drone and live streamed it to YouTube. And our engineers back in the various offices were able to communicate with Jeff real time and basically state, hey, I need that measurement right there. I need you to measure 5 feet away from the girder to figure out how much twist is in the girder. And that was really important because we were actually able to get live data on the call that our engineers could immediately start taking back. We didn't have to wait for sketches, field notes, anything like that. We were getting real-time information that would help our repair efforts. So that was one of the critical successes to the repair efforts there. So with that information and with the knowledge of how big this crack was and how bad the situation was, we had to obviously take a good look at the severity of the situation. We knew the fracture was pretty significant, but we needed to know just how bad was bad. Is the bridge safe? Is it safe to work on the bridge? So we started looking at the various stress levels. And the first thing that we did was we took the original design. Looking at that, we came up with about 38 KSI, which matched the original plans, well below the 0.55 FY allowable. When we then took into account the fracture and removed those sections, we had about 45% of the overall section remaining. Significant loss, as you might imagine. That takes the numbers up to around 83 KSI under P over A, which is obviously well above our 0.55 F sub Y. We're dealing with 100 KSI steel out here, just to give you all a frame of reference on that. So we hadn't even yet accounted for eccentric effects, right? We know from that fracture and what you can see left of that section, it's an L-shaped section. We know there's eccentricities involved with that. So that was a critical thing that needed to be accounted for. We needed a refined analysis in order to account for those effects. So, actually within hours, we were setting up these models and had results the next day looking at what these finite element models were showing in terms of how much of the section had yielded. And you can see from the number of clear elements up there that there was a significant amount of yielding in that cross-section that was predicted. And we saw that in Jeff's inspection as well. We saw the paint cracking and the yielding in those localized areas. With all that in mind, we knew we had a number of unknowns that were still not unaccounted for, right? The actual force in the tie, we knew there was variation there, redistribution of load, transient effects, strength of materials, condition of the welds. There were a lot of things at play that we just didn't know where we were at on. So there were many things. We knew that we were really working with some very, very thin margins in all of this. Our first goal, our first mission was to stabilize the structure. TDOT did a great job of organizing this and saying, hey, we're going to attack this thing in bites. We're going to look at both stabilizing the structure and then a longer-term solution because we knew we had to restore navigation traffic. Navigation was closed down for about 3 days out there. But in thinking about this, there aren't a whole lot of relevant examples for repairing a fractured tie girder that's carrying somewhere around 4.5 million pounds of load. And on top of that, it's partially yielded and distorted. So you've got to figure out how to do this safely and do it quickly. So we did a lot of brainstorming and came up with some solutions. Just a few of the ideas that were considered. We looked at a permanent fix, just jumping straight into that, but that was going to take way too long. Navigation traffic would be a problem with that. Again, shoring towers was a consideration to take some of that load out of the tie, but again, the practicality of getting in there and doing that, the duration, the impacts to navigation, all those things were considered. Temporary post-tensioning, adjacent splices, those were things that we were also considering. Ultimately, we kind of gravitated towards a longer splice that you can see down there in that lower right-hand corner of the screen. So with that preliminary design concept, we began to look at readily available materials. We started scouring the industry, working with NSBA, working with local steel fabricators to figure out what was available. We quickly located with Stupp Bridge. They had a healthy stock of HPS 70 steel in Bowling Green, Kentucky, and they were very eager to help out. So you can see there some of the material that they were fabricating in their shop. Obviously, it was very important that we design our repairs to consider what we could get our hands on. It didn't make much sense to design something that we couldn't get in this type of a situation. So all of this is going on in the first week. You know, the find occurred on Tuesday, and by Friday we had draft plans that were ready for fabrication. We'd already sourced the material for stabilizing the splice. That same Friday, TDOT led a contract and advertised for contractors for part of a CMGC procurement. This was a big step for our project, big step for the repair efforts in order to get some good constructability input. And by Monday, TDOT had selected Kiewit, and they were on the board. They were selected, they were on the ground running really quickly, dove right into the meetings, and were a huge part of that. So once Kiewit was on board, they brought that constructability input to the team. They also brought a very heavy appreciation for risks. You know, as a contractor being out there in the field and executing this, they obviously have a lot of skin in the game. Their focus was to identify and reduce risk wherever possible. And that was an important thing, you know, as it would unfold and kind of help shape the project. So from day one, we were all a bit uneasy about this fracture. And we went through the analysis and how heavily stressed we were. I don't think anybody was too excited about getting out there and rattling these connections. So they had that same concern. So we began brainstorming again. How can we make this better? How can we improve it? So that led to a few design tweaks and design changes there once they got on board. Really what we ended up doing with that is we looked for ways to extend those connections. So we maximized the length of the inboard splice and we maximized the length of the outboard splice based on the materials that we could get. That put those bolted connections further away from the splice and made it much less sensitive to working in that immediate area. So with that direction in mind, we put that into action. We immediately revised our plans, revised our analysis, calculations, and plans were released for fabrication the very next day. So fabrication began just 10 days after the discovery, and Stupp Bridge worked around the clock cutting plates and pre-drilling holes. TDOT picked up those plates and delivered them on that very Saturday following their work. So really very fast-paced fabrication and things were moving through very quickly. And then one of the changes that Kiewit also brought with that, when we advertised this contract, we were anticipating that a lot of the work would be performed from the river just because of the concern with putting additional loads on the structure. Kiewit had an idea to come up with to use a series of chain falls to actually position materials out there on the bridge so they could keep heavy traffic, heavy equipment off of the bridge. By using these chain falls, they were able to actually swing the plates into positions and limit the loads that were out on the bridge. Now, obviously, we had to come up with what was a safe working load that they could be working under, right? Well, you know, through the course of the events, we'd come to find that the fracture obviously didn't happen a minute before the inspector got out there on the bridge. We knew it had a little bit of history. As things were starting to unfold and the media was getting a hold of pictures and things like that, we were tracing the crack back to maybe as early as 2015 or 2016. So knowing that it had been out there for some length of time gave us a little bit of confidence to be able to put some loads in there, but still, we wanted to err on the side of caution. So loads were limited to a single 80,000-pound loaded truck equivalent, and that's what the contractor had to work within. So in the end, no work was performed from the water, and the installation of the Phase 1 stabilization plates was completed 2 weeks after the initial discovery. Here's a couple of additional photos of the Phase 1 repair. You can see the outboard plate there in the top photo and the bottom photo. There's a couple of stiffening tees that were added there, again, because of the offset that we had in terms of the connection plates. That actually induced a little bit of a moment, or would induce a moment if that plate was engaged. So we wanted to account for that and make sure we weren't crushing or yielding the box in any way, shape, or form in that. So let's step back to the Phase 2 design repair. I mentioned that these things all happen simultaneously, so I'm going to take you back to day one. And on day one, you know, our charge was to preserve the capacity of the existing tie. TDOT wanted to make sure that tie was as strong as it was day one, so that was our challenge in the beginning. And this was a real challenge because the bridge was designed with some very thin sections out there. Hazlitt and Erdahl is kind of famous for actually slimming up their designs, and they were using very minimal amounts of steel out there, lots of plate changes, and that introduced a number of welds. So they had doubler plates at each one of the connections. So if you think about it, these tie segments were 75 feet in length, and at each end there was a thicker plate because the net section couldn't handle all the bolts that they were throwing into it to make that connection. So at each one of those upsized connections, you've introduced a weld. And understanding all of this, we began to devise a scheme that really helped to work around that. So we looked at a number of different ways to potentially post-tension this bridge to take a lot of that load out of the tie. But we had to look at, not only bars on the top and the bottom, we looked at bars on the sides, all different configurations, because we had to figure out how best to put this thing together. Mind you, Kiewit's not on board at this point in time, so we're working through this and trying to get to a good solution. Ultimately, we determined that the load path was going to have to be carried in the same way that the bridge was carrying it, which is essentially the web plates are carrying about 85–90% of the load, so that's where the strengthening needed to be. With that direction and those net section issues, the desire to restore the full capacity of the tie, we were initially planning to remove the entire tie and replace it, that full 75 feet. Well, with the addition of the strengthening plates going beyond one of those connection points, that now involved a second section of tie, so it would have been about 150 feet. And when that kind of came to fruition and we started looking at what that looked like on paper with the bridge held together by a bunch of banjo strings, that didn't look like such a great idea. So again, being risk averse, we worked with TDOT and we tried to figure out, and Kiewit, and try to figure out some additional solutions. So that ultimately grew into the idea to plate over and go back to the connections. And that's what we ended up moving forward with, was the idea of sandwiching that existing plating out there, providing some additional redundancy, and tying that back into the original connections. So to use that methodology, we wanted to get as much load out of the existing tie as we could. We wanted to be able to engage those strengthening plates that were being added onto the outside so they would act more compositely. So we devised this PT system that you see in the Bim model up there to really capture as much of that load. It was designed to carry nearly 2 times the dead load of the structure. Again, by the time you get your jacking forces and everything else in there, you get some pretty good factors of conservatism on there. Incremental jacking was going to be used with 4 rods stressed simultaneously, 8 rods total, to concentrically unload the tie. And these are all 3-inch diameter PT bars that are being used out there. Again, about 4.5 million pounds worth of load is what the original dead load was. So here's just a quick shot of our 3D BIM model. This was something that was very useful. Again, this was one of those things that we made the decision to start on day one, and it proved to be extremely beneficial, not only for relations and media outreach and things like this, where you could visualize it, but it also became very important for clash detection. It was very important in part of the design, and we actually cut plans using this model. So really kind of a key part of the process here was to identify some of the challenges and detect clash with this model. In terms of the PT and how we attach that to the structure, we'll walk through some of the details here, but this is one of the things that we had to do in order to tie back into the existing connection. And again, the sections that we're going to strengthen, if you're looking at this picture in the middle, the sections strengthened are to the right. We're tying back in with the whalers and everything on the left. Each one of those existing bolts had to be replaced one at a time with an A490 bolt. Now, in order to then get that bolt through into the weldment, we had to essentially put a cheese plate over top of those nuts that would sit there and act as a spacer between the weldment and the existing tie. So you'll see those details here, but that was the fill plate that you see on the right-hand side. And here's some of the details of the anchor plate and the whalers that are shown up on the screen. On the far-hand left-hand picture, that's the weldment that attaches directly to the tie. You can see in the right-hand picture the whalers that attach to that and then bear against those weldments. And we added in some pipe struts at the end of this assembly in order to make sure we weren't crushing the box due to any of those kind of out-of-plane forces as part of that. Stressing was performed by DSI using their standard jacking system. They used 4 900 kip jacks in all in that concentric arrangement, jacking all 4 jacks simultaneously. Loads were monitored to keep those within specified tolerances and ensure that everything was remaining concentric with the box. So in addition to that, Kiewit worked with DSI and WJE to come up with a comprehensive monitoring plan. Sensors were placed along the structure in order to monitor key locations They used their Dynaforce sensors to actually measure the amount of load in the post-tensioning rods as well as the gauge pressures. So we had a pretty robust monitoring plan out there to make sure we knew the loads that were getting into the structure. But in addition to that, we had sensors located outside of the jacking so that we knew how much the rest of the structure was actually feeling there. So we wanted to make sure that we weren't in any way, shape, or form putting this bridge through more load in fixing it than it could have possibly been designed for or had seen to date. So that was an important part of the project. Those stressing operations started on Sunday, which was Father's Day. And on day 2 of the stressing, the fracture was actually removed. Now this gave us our first real glimpse at the culprit for this situation that we were in. The right-hand photo shows the 2 halves of the fracture side by side, and it was pretty clear upon the removal that there were issues with the weld at this location, and we'll touch a little bit more on that at the end of the presentation here. The phase 2 plating was, again, designed to be fully redundant over the full 150 foot of length of the repair. Fabrication was 2¼ inch grade 70 plates done by AFCO, and all in all, it took about 10 days working around the clock to complete the phase 2 installation. The biggest challenge at the end there was just getting the box back square. So again, everything was being plated, bolted up to that. The plates were loosely hung, and then the iron workers came up with a little ingenuity out there in order to figure out how to square this thing up with some come-alongs, which was a really creative system that brought it to within about a 1/4 inch of square. And then here's the photo of phase 2 completed in all of its glory there. So in order to ensure the bridge was fit for service, though, we've got about 400 welds out there along the length of this bridge. RDOT wanted every single weld on that tie visually inspected and inspected with NDT. So this was a huge undertaking. It actually meant that close to about 500 welds, when you consider the upper truss, ended up being tested as well. So HNTB performed the visual inspection and enlisted the services of CAN USA to perform the NDT testing. Phased array was used on the tie. The upper truss was inspected by Michael Baker as part of our continuing contract, and then the NDT was performed by Fickett using conventional NDT there. So again, I mentioned that fracture. Once it was removed, it was actually sent up to WJE's laboratories for forensic evaluation. So they really put it through the ringer. And once they got their hands on it, they noticed and they identified a couple of additional surface breaking cracks on the inside of the specimen. This was huge because this was kind of the first signs that we had seen. We were doing some NDT out in the field, but this was really important because it allowed for some correlation between what they were measuring in the field and what they were seeing in the lab. So gave us a really good opportunity to use that phased array to see if it would pick up some of these surface breaking cracks. And what that actually showed was that the hydrogen cracking found was detectable, but it would show a really low amplitude. So it might not trigger that immediate concern of what was out there. So that helped us to calibrate the NDT and helped us to evaluate whether or not we were finding what we needed to find in the field. That said, we did map all of the defect locations on there, and those were remedied as part of the phase 3 repairs. The red circles shown up there are showing some of the smaller defects that were able to be cored out, while the blue lines indicate where some strengthening plates were added over larger defects. All in all, we added about 17 strengthening plates. You can see some of the details in these photos. On the left-hand side, you can see one of the even joint repairs, and on the right-hand side, you can see the odd joints there. And there, they're flying some of that steel in. Again, this was done with a little bit more heavy equipment because obviously the bridge had been repaired in the strengthening of phase 2. And with that, the combined 3 phases of the project were then completed within that 83-day total closure, with the bridge being returned to service with no restriction of load. Now, just a little bit in the last few minutes here that I've got to talk through this. I want to talk about the forensic analysis that WJE conducted. Again, going back to those 2 very suspicious looking welds, they focused in on that and later determined that these were hydrogen cracks which had formed during the fabrication of the bridge. Looking at those a little bit more closely, the image on the left-hand side is a slice through the tapered plate, and what's probably immediately noticeable to you all is there's a vast difference between the left-hand image and the right-hand image. The right-hand image is a typical weld. The left-hand image is the weld at the site of the fracture. You'll notice the width and the difference in that. The other thing that you might notice as well is if you look real closely, go back. If you look really closely at the direction of those weld beads, you can see that in the picture on the left, the weld repair, When they would have fabricated this, they would have laid the flat side, the outside face, on the shop floor, welded from the inside, and then flipped it over and welded from the outside. That was the process for the typical weld that you see on the right-hand side. On the weld repair, again, the size and also the fact that the weld beads are coming from the inside in the predominant direction indicates that it was repaired in that sense. So again, we knew that this was a shop repair, and that led to some of the concerns there. Again, going back to the 70s when this was fabricated, there weren't as many restrictions on FCM fabrication. You were dealing with not as much knowledge in terms of restraint cracking and things along those natures, so that was keenly important. And then here on the screen, you'll see another location. These are actually, different magnifications of the same crack, but essentially these were some of the hydrogen cracks that were located in one of the cores that were taken out of the bridge. So this is what we were looking for on the inside of the box, and this was critical because at each one of these locations where these welds existed, they were not accessible to inspectors. There was no way to find these cracks on the inside of the box because they had enclosed this with diaphragms at the end of the bridge, making it inaccessible to inspectors. The only way to do it was through NDT. So with all of that said, what did WJE make of all this information? So based on the physical conditions noted, the yellow portions that you see up there on the screen, that was the primary pre-existing crack location. A pretty substantial size crack, looking about 6 inches in length overall. The green location represents a secondary pre-existing crack. So essentially you had 2 weld repairs at the same section, both having hydrogen cracking issues. During some period of time, years later, the bridge experienced an event, a combination of low temperature, high stress, combined to indicate that first fracture that's in blue right there. And if you look really closely, that blue doesn't go and penetrate all the way out to the surface, the exterior face of the steel. So there was a crack that formed internally to the box prior to any exposure externally that could not be seen through hands-on inspection. Then another fracture event occurred around 2015 or 2016. The exact timing isn't known. That's what's represented there in orange. So that crack occurred, again, due to likely a combination of low temperatures and high stresses. And then finally, the pink shading shows that the fracture propagated sometime between the 2019 and 2021 inspection, running up the rest of the web and across the top of the box, eventually arresting itself in the web to flange weld on the other side. So all in all, that is the failure mechanism that led to the emergency on the Hernando de Soto Bridge. And I guess just a few lessons learned here to wrap it up. This was the 4th emergency project that I've had the experience of working on or being involved with. And I really continue to be amazed at the collaboration, how everybody pulls together and works together in times like this. There's no finger pointing. It's everybody focused and working and trying to do the best that they can, working together. So everybody working for a common good. Again, projects like this require incredible amounts of communication, so you have to really accept that, embrace that, and plan for it. There's just no way around it because there's just a lot of information that has to be disseminated to a lot of different people moving in different directions. So TDOT's decision to use the CMGC process was really a pivotal one. That brought a lot of positives for the project, and in my opinion, CMGC is a really good approach for using for rehabilitation of projects. I think there's a lot of value to be gained there for major structures. And then just lastly, be prepared for just about anything because you'll get thrown a lot of curveballs on a project like this. And I'll leave up some quick stats on the project. Overall cost of the project was about $9.7 million to repair the bridge, 200,000 pounds of structural steel, 9,000 bolts, and we took about 1.2 million pounds of tension out of the tie before we reattached the plating. So 1,200 foot of welds were inspected as part of this bridge. That's all I got.
Good afternoon. It's not really a question. I just wanted to thank the team for allowing Resensus to be part of their team. We supplied all of the sensors. We installed about 45 wireless sensors in 48 hours.
What was the total time to from start to finish to complete the project?
To complete the project was 83 days from start to finish, from the finding of the fracture to open to traffic.
All right, let's have a round of applause for Aaron. Thank you.
The preceding was produced by the National Center for Pavement Preservation. More information can be found on the web at pavementpreservation.org. Additional support provided by Michigan State University.